All right, section 10.1, counting. And counting is part of any probability course. We're not going to get into the probabilities, but we're just talking about the first couple of sections in this section. So 10.1, counting. Objectives: find all the subsets of a set, count the number of elements in a set, solve counting problems using the multiplication principle. All right, so a few objectives here. I'm going to read this whole thing to you. They talk about the empty set. It's the subset of all sets. That's interesting. You have a proper subset, meaning the two sets aren't the same size. All right. Just the idea of a subset, but I'm going to not lecture on that topic, but this is what I'm doing. All right. Well, this will be easier later, but they're saying find all subsets of a set. Write down all subsets of the set containing M or LMN. And they wrote them down. There are subsets with 0 elements is 1. There's one of them. It's the empty set. Subset of 3 elements. Now notice they said subsets, and this is the actual set itself. So that's not a proper subset, but just the way we use the phrase, use the word, the element itself is a subset of this. So it kind of looks like this. A is a subset of A, but A is not a proper subset. So that little subset symbol with a line under it means they could be equal. All of these are proper subsets. So these two elements, these 3 sets with 2 elements each. Gives you that. And there's something else we're about to find out. The number of terms in this, number of elements, is 3. And that means the number of subsets is 2 to the 3, or 8. So do you see the 8 subsets, including the set itself, 1, the empty set, 2, plus 3 more, plus 3 more, 8. There are 8 subsets, so you don't have to worry about listing them correctly. You know the number of subsets. They give that to you here. If A is a set with n elements, then A has 2 to the n subsets. So I gave another example. A, B, C, D, E. The number of elements is 5, so there are 32 subsets. That's a lot to list, but we know that there's a subset of size 0, and that is the empty set. And there's just one. That's it. Subsets of size 1, there's A, B, C, D, and E. All right. Putting this braces around it gets tedious, so I'm going to stop doing that. But subsets of size 2, I'm not going to try to list them all because there's more of those. There's A, B, there's A, C, there's A, D, there's A, E, B, C, you get the idea. Subset size 3, but I'm going to talk about subsets of size 4 because there's something interesting about the number of subsets of size 4, and I want you to see it. So there's A, B, C, D. What did I do? I left out E. There's A, B, C, E. That time I left out D. A, B, I believe that's C. A, B, D, E. Leave out B, A, C, D, E, and the only one I have left out is A, so that would be B, C, D, E. Notice there's 1, 2, 3, 4, 5. Same as 1, 2, 3, 4, 5 for the number of subsets of size 1. So if you ever get into sets, one thing I want you to think of is if you're asked to find subsets of, say, size 4, one way to think about subsets of size 4 is by thinking about what we call the complement. If you pick a subset of size 4, what you're really doing is leaving one term out, if you have 5 terms. So the set A is similar to the set B, C, D, E in that if I remove A from the original set, this is the one I'll get. So there's a name for, 2 sets that do something like this called the complement. But without getting into that detail, I just want you to know that the number of subsets of size 1 is usually pretty easy for students to see. They, it's just 5. Well, the number of subsets of size 4 is created by removing 1. And how many ways can you remove 1? Well, you can remove the A, you can remove the B, you can remove the C, you can remove the D, you can remove the E. It's also 5. So only going to be one subset of size 5, and that's the entire set. And that kind of agrees with there's only one subset of size 0 where you remove nothing. So there's 1, there's 5. Haven't figured out how many there are here, but I know if there's 32, I can figure out how many of each of those there are. And that helps if I ever wanted to list all the sets. We really don't do that very often, but I just wanted you to know there's a lot of thinking that you can use rather than just trying to list all of the subsets. All right, well, it seems like a change of topic, but it's talking about how sets interact. So let's look at this question. It's called a survey problem. In a survey of 100 college students, 66 were registered in college algebra. 42 were registered in computer science 1, and 12 were registered in both courses. How many students were registered in college algebra or computer science 1? This word "or" is a mathematical word, and so we want to use that language the way it's meant here. And then what else? How many were registered in neither course? All right, so we're going to do something called a Venn diagram, and the book will have a better one, but let me just kind of start it out. This is a general kind of Venn diagram. And one thing the book doesn't do, but I'm going to add that to the better diagram we're going to see, is I like to put numbers on the borders themselves. What does this 100 mean? It means that everything inside here totals 100 students. 66 were registered in college algebra. So if this is college algebra, I personally would put a 66 there. And 42 were registered in computer science. So I put a 42 there. Now, putting numbers on the border is not standard technique. That's more of a thing that I do, did as a tutor and do even now on problems like this. But what we're really interested in doing is finding the values inside these regions, these regions shaped from the circle. So 66, that spans 2 regions. It's the number of students who took college algebra without taking CSIT, and there's college algebra alone, plus the numbers who took both courses. So we'll see how the author lays this out. If A is the number of students who took college algebra, again, pretty non-standard, but I would put 66 on that circle itself to remind me that the total sum is 66. By the way, let me cross this out so you don't know it's there. Universal set is 100. What about B? B is the number of students who took computer science. According to the question, they just gave us that number, 42. And then they told us that the number of students who took both classes is 12. Now that doesn't belong in on the rim of anything. That's this area right here. This area is representing, great, okay. This area is representing the number of students who took A intersected with the number of students who took B. So this 12 should be written down where they wrote it down. Well, how do I uncover that little value right there? Well, if I have 66 total inside the circle and 12 of them are here, it's just 66 minus 12. That's how I figure out that this is 54. If this circle contains 42 and 12 of them are here, that tells me that 30 are there. So think about the questions I could answer with this. We're doing this to answer just one specific question, but let me cover up that 4. We still don't know that. We haven't figured that out yet. All right. What questions could we answer? We could answer. They could have said, of the 100 students, how many are taking college algebra alone? You know, or taking college algebra but not taking computer science. And that would be 54. 12 are taking both classes, but 54 are taking just college algebra. And 30 are taking just computer programming, computer science. So we could answer those questions. But their question was, how many, let me see how they write. Oh, how many were registered in college algebra or computer science? All right, now I said that was a mathematical word. So what does that mean? It means if you pick a student and the student is registered in both, we would say, oh, you qualify, you're registered in college algebra or computer science. If a student is only registered in computer science, we'd say that was a success. If the student is only registered in college algebra, we'd say that's a success. The only students who would not be in this list would be the students who were somehow out here where they were in neither college algebra or computer science. So what we want to do is we want to add these three numbers together. The number of students who are in college algebra or computer science, or the number of students who are just in college algebra, the number of students who were just in computer science, plus the number of students who were in both. And what is that, 96? So we get 96 students. Now, the good news is there was a way to figure this out. There is a way to figure this out without going through this much work that they're going to introduce to us in a moment. But I still like these little sets. Well, by the way, if 96 students are contained in these 1, 2, 3 regions, then that means that there must be, of the 100 students, there must be 4 that are not in either class. And I got that from taking 100 and subtracting the 96 that I had right there. I don't think they told us anything new here, but here's what I want you to see, this formula. All right, so how could we have done this? How could we have calculated this with a shorter technique, an easier method? Well, union is what we mean when we say or. We mean the union of sets. So the number of students in college algebra, I'll say algebra, union computer science, is the number of students in algebra, which was 66, plus the number of students in computer science, which I will say, which was 48, as I recall, 42. 42 minus the number of students in both. And that's what this means. When we say A intersect B, we mean the students in both. Actually, I should have written that here. The line I was working on had numbers. Number in both was 12. All right, so hopefully this formula is just, well, I'm just using the formula they gave us, so I can apply that formula rather than this elaborate series of circles and everything to this question. 66 were in college algebra, 42 were in computer science, 12 were in both. So it's 66 plus 42 minus 12 according to this formula. Now, why does it work? Well, here we're counting the number of students in college algebra. Here we're counting the number of students in computer science. But notice I counted the students who were in both twice. I counted these 12 students here, but I also counted those 12 students there. So I just want to subtract what I counted twice. Well, this is 30. Yeah. So I get 96. The same 96 I got by adding these three numbers. So this can be a very powerful way of counting. That's exactly what we're trying to do. Not our main way of counting, but just be prepared to do that if we had a problem. Now, what they're saying here is if the number of students, if the intersection is the empty set, what that means is the number of students who did both is equal to 0. Then that, remember, minus the number in both, well, that just drops out. So when you have a situation where there is no overlap of the two sets, then the number of students in A or B, A union B, is just number in A plus the number in B, and you don't have to do any subtraction. You don't have to do any subtraction if there's no overlap, if they have no elements in common. So they give you that as a separate formula, and extend that. So extending that formula, A1 union A2 union A up to AN. If they have no elements in common, you can just add the terms separately. That's not what's going on here. All right. This is another rule called the counting rule. Let me find the formula first here, and then we'll go back and use that. So this is called the multiplication principle, and they use the word task. Like you're going to do something, then you're going to do something else, then you're going to do something else. And so if a task consists of sequences of choices in which there are P selections for the first choice, then Q selections for the second choice, and then R selections for the third choice, and so on, the number of ways to do the entire task is arrived at by multiplying the individual counts, the individual numbers. So it's the number of ways to do task 1 times the number of ways to do task 2 times the number of ways to do task 3. So we didn't have that formula when they did this, so they spent a little bit more time with this. But you're at a fixed price dinner, and it provides the following. Super salad, so that's 2 choices. Entree, fried chicken, steak, vegetarian, 3 choices. For dessert, there's 1, 2 choices. So this is what we mean by task. The task 1 is select soup or salad. Task 2 is select your entree. And task 3 is to select your dessert. How many ways could I have put a meal together? Well, it's 2 times 3 times 2, which is 12 different ways to put a meal together. That sounds like a lot, 12. There are 12 different varieties. But, here I picked soup, steak, and chocolate cake. Another one could have been salad, steak, and chocolate cake. And that would be a different overall meal experience. So it would be a different meal order in that case. So with that rule in place, we know the calculation. All right. They went and listed all of them and tried to keep it organized by something called a decision tree or tree diagram. So the first decision is, are you going to get soup or salad? It creates a node. Then the second, another decision point is, are you going to get chicken, steak, or vegetarian? Chicken, steak, or vegetarian? And then at the final decision is, are you going to get pie or cake? And this way of organizing it gives you all of the lists. And if you counted it, there'd be 12 there. So counting, the whole point of this is counting frees you from having to actually make the list. And counting theory can do things for us that could be a lot of work otherwise. How about this one? How many 2-symbol codes, so there's just a very short code or password, can be formed if the first symbol is a digit. So when they say digit, there's 0, 1, 2, up to 9. That's a total of 10 characters. 1 through 9 is 9 characters, but with a 0, it's 10. So there are 10 digits. And the second symbol is the first letter of a color from the choices red, yellow, green, blue, purple. So I like to put myself into this, like, all right, let's make a code. Let's say I picked 6P. Now, how many choices did I have for that first part of it, the digit? Well, it turns out I had 10 choices, because I could have picked 0 through 9. How many choices did I have for the letter? 1, 2, 3, 4, 5. I had 5 choices for the letter. And the theorem that we work with, right, is that we know we multiply these together. So there are 50 possible codes with this particular restriction. 10 choices for the digit and 5 choices for the letter. All right. So that's it. That's our section on counting. The next section takes it to the next level, but this is a very important base for that level. So make sure you understand that what we're doing when we're counting and some of the rules that we applied. See you in the next video.